Now, linear versus nonlinear behavior. Stress and strain follow a generally linear behavior. When stress is applied and then removed, elastic strain recovers first, then viscoelastic. A lot of times, a little bit of strain remains. We call this creep. That's why, for example, a rubber band wears out eventually. It loses some of its elasticity. It's like, a really old pair of sweatpants. The waistband doesn't snug around your waist as tightly as a new pair because there was creep happening in that elastic. Not all of the atomic bonds recovered completely. If even a couple break or a couple of molecules slide past each other a little bit, because even though it was almost completely elastic or viscoelastic, there was a little bit of that elastico-viscous behavior going on. Just a teeny tiny bit is creep. The relationship is nonlinear with elevated temperature and pressure. We start getting more viscous, less elastic behavior. So less and less return. It's no longer just creep, it's straight up viscous behavior. So as the temperature and pressure increase, less elastic, more viscous. So this is all cool. We talk about bungee cords and Play-Doh and silly putty. What about real life for a geologist and an engineer dealing with rocks? Because the world is not made of bungee cords. It's made of rock. That's why we do experiments with real rocks. Because we want to know, how does the rock behave? How do different kinds of rock behave? So we do experiments with them. We observe the behavior of rocks rather than all of these different analogs or substitutes. And we can vary the parameters to see what happens. There are different types of experimental parameters to keep track of and or change. We can measure the deformation. We can measure or change the confining pressure. We can vary the temperature. We can vary the strain rate. Strain rate can have a huge factor or a huge impact on deformation. Take a piece of glass. If you have a sheet of glass, supported on a couple of blocks or legs on either side, and you take like a small rock that weighs like a pound, and you set that rock gently on the glass, very low strain rate, the glass will probably support it just fine unless it's an incredibly thin, weak piece of glass. But like a window pane, you set that 1 pound rock on it, gently, no problem. No deformation. You lift that rock a few feet above the glass and let go of it so that it's falling, hits the glass abruptly, very high strain rate. All of that strain is applied instantaneously, just like that. The glass deforms. It deforms brittly and shatters into a bunch of pieces. Strain rate definitely has a huge impact on what kind of deformation happens. Another one is silly putty. If you pull on the silly putty slowly, it stretches. It deforms viscously. If you pull your silly putty very rapidly apart, it just snaps in half. It deforms brittlely. Strain rate is incredibly important. Pore fluid pressure, also incredibly important. This is going to come up a few different places in this semester. Pore fluid pressure can dramatically change the properties of a rock. We'll see it in Mohr circles, we'll see it in fault movement, we see it in rock fracturing. More and more pore fluid pressure makes things happen more and more easily. The fault can move more easily, the rock can break more easily. And work, hardening or softening, what's happening.